Hello there, I am Ümit Alkuş. In this video, we will solve one problem in Chapter 8. The system in the figure is initially held at rest and the spring, whose spring constant is K equals 300 newtons per meter, is neither stretched nor compressed. There is no friction between the box and the inclined plane. Now the system is set free to move. A. What is the speed of the box when it has moved 5 centimeters down the incline? According to the figure, for positions 1 to 2, from the right triangle, height A is equal to d times sine theta. The conservation of total energy is written to be. Now let us choose position 2 as the zero potential energy level. The potential energy of the box at point 1 becomes m times g times A. The kinetic energy at this point is 0 because its initial speed is 0. And the energy stored in the spring at point 1 is 0 because it is neither stretched nor compressed. The potential energy of the box is 0 at point 2. The kinetic energy is 1/2 times m times v squared. Finally, the spring energy becomes 1/2 times k times d squared because the spring stretches. From this equation, we can have an expression for the speed at point 2. Here, A is equal to d times sine theta. Now, we substitute the numerical values into this equation. Therefore, we obtain approximately 0.63 meters per second. Part B. How far down can the box move before momentarily coming to rest? For positions 1 to 3, according to the right triangle, we have height B equals distance d prime times sine theta. Now we write the conservation of total energy as follows. It is suitable to choose point 3 as the zero potential energy level. The potential energy of the box, according to this figure, becomes m times g times B. As we discussed in Part A, the kinetic and the spring energies of the box at point 1 are 0. The potential energy of the box at point 3 is 0. Its kinetic energy is also 0 because it is momentarily at rest at this point. Finally, we have the spring energy at this point as 1/2 k times d prime squared, since the change in the length of the spring is d prime. Here, B is d prime times sine theta. D prime is common at both sides, so we obtain. From this equation, we get an expression for d prime as. Insert the numerical values into this equation. Therefore, you get 0.10297 meters, or approximately 10.3 centimeters in 3 significant figures. Part C. The connecting cable suddenly breaks when the box stops momentarily so that the box slides down the incline freely. What is the speed of the box when it reaches the ground? For positions 3 to 4, we have height C as h minus b, where height b equals distance d prime times sine theta. Anyway, we write the conservation of total energy as follows. We choose point 4 as the zero potential energy level. Then the potential energy of the box at point 3 becomes m times g times c. The kinetic energy of the box at this point is 0, since it stops momentarily at this point. The potential energy of the box at point 4 is 0. And the kinetic energy is 1/2 m times v squared. As you notice, we didn't write the spring energies, since the cable broke at point 3. From this, we get an expression for the speed at point 4 as... Now we write the expression for c with the corresponding numerical values. Therefore, we obtain the speed of the box when it reaches the ground as approximately 5.27 meters per second. Okay, that's all about this problem. Thank you for your attention. See you in the next video.